Okay, year 11s, let's consider the factors affecting the rate of reaction. So we'll give ourselves a heading. Factors affecting reaction rate. So guys, there are 5 key things that affect reaction rate. The nature of the reactants, the concentration of reactants, the temperature in which the reaction takes place, the surface area of reactants, and the presence of a catalyst. So the nature of the reactants is generally alluding to whether or not something is in an aqueous solution or a gas, and I will leave you guys to read over that in your textbook at another stage. But this morning I wanted to discuss with you concentration, temperature, surface area, and catalysts. So the first one of those is concentration. So if you increase the concentration of a solution or of particles in a solution, then generally speaking, you will increase the rate at which a reaction will occur. So for example, I've got these 2 beakers here. Now this grey bit down here represents some magnesium, and the solution is a solution of hydrochloric acid. On the left hand side, we've got a reasonably weak solution, so we can say that that is 0.1 mole HCl. And on the right hand side, we can say that it's much more concentrated at 2 moles of HCl. So if you increase concentration, then by definition you increase how many particles you've got of something in a solution. So the red bit here, guys, is representing a hydrochloric acid molecule, and the same for the left hand side. You can see that in the concentrated beaker there is much more presence of those HCl molecules. So we've got, as a result of concentration, we've got more particles. Naturally, if you increase the number of particles that you've got, then it makes sense you will increase the number of collisions that you have between these particles and between the magnesium strip that you've got down here. If you increase the number of collisions due to the presence of more molecules and more particles, then fix that up. So you increase the number of collisions that you have. Sorry about my writing on this, I'm just getting used to it. So you increase the number of collisions. Now that's not to say that all of the collisions in here will be favourable in terms of energy and orientation. But if you increase the number of those collisions that are occurring, then you will increase the rate of having favourable ones. And if you increase the rate of favourable collisions, then invariably you will increase reaction rate. So that's the first relationship for today. An increase in concentration will cause an increase in reaction rate. So that can probably just be represented by increase in C equals an increase in reaction rate. So that's the first one that we need to look at. The second one is going to be temperature. So if you increase the temperature in which a reaction is taking place, then you will usually increase the rate of reaction. Now I've sort of commandeered 2 pictures from a previously arranged PowerPoint that sort of demonstrate this a little bit for us. So here on the left hand side I might have something that is at a reasonably low-ish temperature, let's say kind of room temperature, so about 25 degrees Celsius. Not room temperature in this freezing cold weather, but if we have the heater on. And let's say that this is occurring at 50 degrees Celsius. So you can sort of see here that these streak marks represent that if you increase the temperature of the system, then you increase the kinetic energy that the particles in that system have. And if you increase that energy, two things are going to happen. They, A, collide more often, and B, they collide with a greater amount of energy and thus have more chance of having an energy higher than the activation energy. So if you have those two things, more collisions and higher than activation energy, then you increase your ability to break the bonds of the reactants and thus form more products at a faster rate. So that is the second relationship for today, is an increase in temp is going to cause an increase in reaction rate. So that's relationship number 2. The next one that we have to look at, I think we'll go with white background for this one today, is the effect of a catalyst. So the human biologists amongst us will know that the enzymes in the human body act as catalysts, and it's a good thing we've got them because we couldn't survive without them. So, guys, as we've been drawing a lot of these diagrams lately, all reactions need a certain amount of activation energy. So if I can draw this like that. First of all, is this an endothermic or exothermic reaction? Think about that for a minute while I put in products and reactants. Then, guys, we know that the activation energy, so the energy required to break the bonds, is all the way up here on the top of this curve. Now, I think we'll just select red to highlight this in a little bit better. If we draw an arrow all the way up there to this activation energy, that's the energy that's going to be required by the particles in the reactants to break their bonds, get to this transition complex, and form some products down here on the right-hand side. Sometimes, year 11's, this activation energy is too big and it doesn't come naturally or easily to these reactants. So we can put in to a reaction what's called a catalyst. And the idea of that catalyst is to decrease the activation energy of the reaction. So generally speaking, we can just show that with dot points like that. So what the presence of this catalyst allows to happen, is that you have got a decrease in activation energy. In fact, you've decreased it from here to here. And what that means is that you're going to have more reactants with an energy above the activation energy because you've just decreased it a whole lot all the way down here. So you've made an alternate pathway, so to speak, for these reactants to travel on with a much lower activation energy. So the presence of a catalyst will therefore often increase reaction rate because they act to decrease the activation energy required of a reaction. So that is the third relationship for this morning. And the last one that we need to consider is the effect of surface area. Now this is going to be very interesting for me to draw, but as I've drawn for you guys on the board previously, if you have a cube, let's say, of magnesium carbonate, so MgCO3, and let's say that we added some acid. We often forget, I think, about nitric acid, so we'll use nitric acid. So you've got all these particles here of nitric acid floating around in this beaker. It's very hard for the nitric acid to attack all of this magnesium carbonate because you've actually got some magnesium carbonate on the inside of this cube, but the nitric acid has to first wear away what's on the outside to get to what's on the inside. So it's fair to say, guys, that the surface area of this cube isn't all that big. The surface area to volume ratio is very, very small. But if you took a hammer to this cube of magnesium carbonate and you smashed it up into little pieces, then what you do is you expose a lot of the surface of that magnesium carbonate. What then is very easy is the following. The particles of the nitric acid can just come and attack the particles of this magnesium carbonate. It's got more of its exterior sections exposed, and therefore more of that exposed means more collisions. More collisions means an increase in reaction rate. So you can summarize that by doing an increase in SA, surface area, equals an increase in reaction rate. And that pretty much summarizes chapter 11.3. Thanks for listening.